Hello, everyone. So today we're going to continue to build up MO theory by extending it to second row elements. However, it is worth noting that this is quite a big topic because second row elements get a little bit fun. So we're going to be mostly starting by focusing in on sigma bonds. So in order to do this, we're going to want to first start by sticking with the simplest second row elements we can, which is going to be diatomic molecules, because I don't want to have to worry about dealing with more atoms than I need to. So let's start by looking at two atoms, and let's make it a little bit simpler from there. Let's try and make all of these homonuclear. So by saying homonuclear, I'm just talking about two species that are of the same element. So hydrogen, hydrogen, carbon, carbon, boron, boron. Doesn't really matter right now. We're going to try and build our ways from the ground up. But by working with the same exact elements, this means that our orbitals are going to overlap the best because they're going to come in at the same energy, which, as you've seen a little bit when we were working with hydrogen, can be a fairly important factor. And to make this a little bit more straightforward, we're also going to try and focus on building up MOs from similar atomic orbitals. So we have a set of 4 atomic orbitals. So we have our S, our PZs, our PXs, and our PYs. So kind of like we've done before, we're going to focus on just PZs overlapping with PZs, and S's overlapping with S's, X's with X, Y's with Y's. This is partially because they're going to have the best overlap or ability to connect with each other. It doesn't mean that you can't have a mix and match of orbitals. It just tends to be these give the lowest energy, and we'll get into a little bit more detail of why a little bit later. But what's important to note for us is that when I take each of these sets of atomic orbitals and I let them overlap, this will, just like I did for the hydrogen orbitals, present a bonding and an anti-bonding molecular orbital. So this ends up meaning that I'm going to have 4 orbitals coming in from each of these atoms, so 8 orbitals total. So guess what? We're going to make 8 orbitals in the end. So 8 atomic orbitals produces 8 molecular orbitals. So 8 molecular orbitals is a bit much to handle all at once. So we're going to want to split this up into some easier to look at categories. So one of the easiest is going to be looking at direct overlap. And as we saw with valence bond theory, we're going to tend to define our direct overlap occurring along the z-axis. So the first category we're going to focus in on today is going to be orbitals who overlap along this z-axis. And for now, we're going to ignore those who occur outside of it. So when we want to start with figuring out is which atomic orbitals have a significant amount of character along this z-axis. So we have our simple case, the s orbitals, because guess what? They have character everywhere. And then, of course, we have our pz. And because I have them centered around atom A and atom B, this gives me a total of 4 orbitals. So I took the total number of orbitals I started with, and I literally cut it in half. So this gives me 4 atomic orbitals, which logically should make 4 molecular orbitals. And as we have so far, we're going to start with the simplest approach, which is we're going to build up our 4 molecular orbitals using a set of linear combinations of our 4 existing orbitals. So our 2 S's and our 2B and our 2 P's. So when we're doing this, it's worth noting that our choice of coefficients are going to change how much of each character there, of each atom there's going to be. So if I have a large Ca2s value, this means that my 2s orbital on my A atom is contributing the most character. Similarly, if it's very low, it means it's contributing almost no character to the shape and to the energy. So the real trick of building molecular orbitals is trying to do it so that my total energy for the molecule is as low as possible. And this is going to tend to happen by building a set of very low energy bonding orbitals and then taking all of that unfavorableness and jacking it up into the antibonding. That's what we're really going to want to try and optimize to make the most stable overall species. Now, the problem is that trying to build up a molecular orbital from 4 different atomic orbitals gets a little bit messy. So we're going to start with a pretty easy trick that we'll justify later. And that's the idea that if my orbitals are significantly different in energy, that means they're going to have slightly different overlaps. And we can also imagine this thinking about it a little bit visually. Because remember, this picture is wrong, and my s orbitals are actually much bigger than my p orbitals, which means that they're going to have a much bigger overlap radii, and so they're going to interact first. So my s orbitals are going to have a slightly lower energy bonding and antibonding orbital, and my p is slightly higher. So we can separate these due to their different interaction character and energies. We can separate them out into 2 sets of molecular orbitals. So we're going to have one set that's made just out of s character, and one set that's made just out of p character. And don't forget, each of these sets is in and of itself going to be composed of both a bonding and a anti-bonding set. Because again, 2 orbitals come in, I get 2 orbitals out. And so this is the general idea when trying to build up molecular orbitals. Now we can actually use an extra little bit of a trick, because now I know that my sigma orbital for just the s bond is going to be composed of my 2 s atoms. But in what ratio? This is where going to a homonuclear species can be really advantageous, because if these orbitals are the same exact shape, because they are the same atom, just separated, then this means that they're going to have the same exact character. So as long as A and B are identical, so are my coefficients, where they will either be exactly the same, or in the case of antibonding, they'll be equal and opposite. So one will be positive and one will be negative to help allow that cancellation. But when we can do this, this lets us start building up a full set of bonding and antibonding for both my s and my p orbitals. So let's go ahead and start by examining the lower energy of these 2 overlaps, and that's going to be something that should be a little bit familiar. I'm going to take 2 s orbitals and I'm going to turn them into a bonding and antibonding orbital. So not too much is going to change from when we were doing the original sigma s for the hydrogen atom. The biggest things that are going to change now is just the shape a little. So we'll end up introducing an extra node in the middle, which won't have too many implications, and the fact that they're just going to be larger, and the charge will matter because I'm letting charge vary. But because these are analogous to the sigma orbitals built up from my 1s orbitals, this means that I can use the same notation that we used previously. A bonding orbital is given with Girard symmetry, and an anti-bonding orbital is given with un-Girard. So symmetric and anti-symmetric is going to be the same as bonding and anti-bonding. So because we like low energy things, let's start with that Girard orbital. And again, being bonding, it's going to have a symmetric combination of the 2 orbitals, which is going to maximize overlap here in the middle, which is going to bring my energy way down just like it did before. The real trick here is that it turns out I have a new normalization constant. And the normalization constant can be a bit messy because I first need to figure out that dang overlap integral again, which we'll get to. Similarly, we can adopt our previous notation, and my un-Girard or anti-bonding sigma orbital can be given as the anti-symmetric combination of the 2 orbitals. This means that they will cancel out in the middle, generating a node, and push more of the electron density to the outside, driving my two systems apart. So fundamentally, as I go from 1s orbitals mixing to 2s orbitals mixing, it's only really quantitative changes without anything qualitatively changing by that much. But as I mentioned earlier, one of the important things to figure out if we're going to start is going to be this normalization constant, which in and of itself is going to depend upon the overlap. And it turns out that overlap also controls other things like the energy, and it's going to become a very important feature from here on out. So when trying to understand the interaction in between any of our new sets of orbitals, a good place to start is gonna be these overlaps. Now we get a big benefit because just like with our hydrogen orbitals, both the bonding and the anti-bonding orbitals are going to have the same overlap. How overlap integral, how it gets used is gonna be slightly different. So let's go ahead and take a look at my general expression for the overlap for sigma orbitals built out of 2s uh, atomic orbitals versus those built out of 1s atomic orbitals. So here's our old friend, the 1s atomic orbital. All that we ended up doing was adding in a couple of factors of z to show that the charge of the atom will make a big difference. So the biggest thing you should note is that exponential decay that controls so much. And this exponential decay now factors not just on radii. Again, the overlap will die off exponentially as I move my two atoms apart. But now it's also going to die off exponentially as I increase charge, which should hopefully make sense because as the charge goes up, the orbitals tend to contract. And that means if I'm trying to overlap two orbitals that are getting smaller and smaller, it's gonna get harder. And I have to get closer to counteract this. So if the charge doubles, I practically have to get twice as close to get that same overlap. Similarly, you can apply this same operation to the 2s orbitals. And it's going to have a very similar exponential die-off, but now it's gonna be dampened because guess what? The 2s orbitals are almost twice as big. And we saw this when we looked at radial distributions of the s orbitals previously. But what's also worth noting is the exact shape of the molecule of the atom will change because I have that extra node. And so because I have an extra node, it turns out I have to introduce an extra term. So when we do this, this has some important implications to what happens to the overlap integral as I increase the separation distance. So normally for the 1s, it's going to die off real quick and real smoothly. Makes sense. I'm just having two spheres. I separate them. The integral is going to die off very quickly. But because that 2s orbital is bigger, it's going to die off much more slowly. And you'll notice there's a weird inflection point around here. And that's because roughly this point, I'm passing that node, which causes a little bit of an unusual curve shape change. And so what we end up finding is that this larger distance is going to significantly change my energy and my overlap integral. So my 2s orbital is going to have a significantly larger interaction energy simply because the orbitals are able to overlap more, and so that J term we saw the K term we saw previously, that interaction with that extra density in the middle is going to go up, even though at this distance we've significantly separated that J term, that interaction with the electrons located on the other atom. But what's really useful to note is that after I get to, say, a distance, to a significant distance, what we see is that the 2s orbitals still have strong overlap and strong interactions, where at this point, my 1s is a little bit ignorable. They don't overlap that much, and so they aren't really bonded. And so this idea of the difference in between the overlap in between my 2s and my 1s orbitals is one of the reasons why it's fairly safe to ignore core electrons when talking a lot about when talking a lot about determining uh, intermolecular bonds, because when I'm looking at the atomic overlaps, this guy just doesn't play a role. So all of the action and bonding is really in this valence shell, and it's because of this bigger size and this bigger overlap. And so we'll play around with these overlaps a little bit more later, but for now, it's good to get an idea of the shape and where the electron density is, be it more on the core or as the S gets bigger, more in that middle, more of that bonding character. Or if we're working with antibonding, more of that antibonding character. So that's more or less the what we're going to from now on kind of refer to as the 1s in this contest, because this is the first of our sigma bonds. But it turns out we have another set of sigma bonds, that coming from the P. So your book likes referring to these as the 2 sigma. And similarly, they're going to form an additional set of bonding and antibonding character orbitals. Rather like we saw from the S, the shapes will just change a little bit. As now, my bonding orbital, or the 2 sigma Girard, will give me a overlap in the middle, and then I still have this extra P character node on the other side of the atom. So we are starting to see a little bit of a qualitative change, but again, because what we mostly care about is this overlap in the middle, for now we won't worry about it too much. But if I generate a bonding orbital, turns out I also need to generate an antibonding orbital. So the Ungerad or antibonding orbital is again going to be the antisymmetric combination of my 2p orbitals, again in the z direction for that direct overlap. So fundamentally, I make these orbitals roughly using the same shape, still need a normalization constant, which means I still need an overlap integral to tell me how I can get my normalization constant, and again, to tell me a lot about the strength of interaction, energy, and so on and so forth. So our overlap integral for these 2 sigma bonds gets a little bit longer. And so what's first important to note is that we're going to see this exponential term be the exact same exponential term I saw for the 2s. So we're still going to see this exponential die-off at the same rate. What's going to change a bit is the shape. And the shape of the overlap is, of course, given by the shape of the orbitals, which we can end up expressing with this longer polynomial term. Now, the biggest thing that's probably worth noting when looking at this is that we introduce a negative term in this integral. So in this overlap integral, this negative term represents actually a kind of neat feature, which is at relatively large distances, I'm going to still get some pretty decent overlap. Not quite as good as I did with the S, because remember, my S orbitals are bigger. So I have to get a little bit closer to get the same extent of overlap when dealing with P. But something interesting happens as these guys get too close, because now this positive character can work its way over here and start canceling out some of the wave function over here and vice versa. So it turns out that if I drop my distance really close, so this R term starts dominating, these two groups almost end up exactly on top of each other. And when that happens, it pretty much gives me no overlap as I completely canceled out my system. So this is something to watch out for, that we want to make sure that we avoid getting our sigma orbitals too close. So again, we have this decreased overlap as I start getting too close, and that's something to keep in mind about, because this is the first qualitative change I've seen when dealing with orbitals yet. Because sigma s, there's no such thing as too close except for internuclear repulsions. P orbitals aren't quite so generous. And again, it's because of this nodal character. So with that said, that kind of brings us to the end of qualitatively looking at our sigma molecular orbitals. Next time, we'll start by working with our pi orbitals, because gotta love that indirect overlap. Till then, take care, stay healthy.